And today I'm pleased to share my recent work in 19th Open Forum workshop. And my presentation topic is large eddy simulation and spray model development of liquid ammonia injection on non-flashing and flashing boiling conditions. And my presentation includes 4 parts. The first part is a background. Due to the carbon dioxide absence in the complete combustion, ammonia has gained global attention and being regarded as a clean energy carrier link, which can mitigate the carbon increase and slow down the global warming. And it has relatively low heating value and high liquefaction temperature. Therefore, the storage of ammonia in liquid form is easier. Therefore, direct injection of liquid ammonia is more efficient than gaseous ammonia for energy supply in large-scale applications. However, the special thermal physical properties of liquid ammonia, such as high saturation vapor pressure and latent heat, introduce the flashing boiling phenomenon and significant cooling effects. The flashing boiling means that the local pressure drops until being lower than the saturated vapor pressure of the liquid. And as shown in these 2 figures, it can be seen that the ammonia is more prone to enter the superheated region than other traditional fossil fuels. Therefore, it is essential to construct a uniform spray model accurately describing the optimization mechanisms under wide conditions from non-flashing to fully flashing boiling. And this is also the aim of this study. And the next part is about the model construction and computational details. The key parameter RP superheat degree is firstly defined, which is the ratio of the ambient pressure and to the saturation vapor pressure under the liquid temperature. And the conditions with RP 1.5, 1, 0.5, 0.3, and 0.1 are included in this study. And due to the wide thermodynamic conditions involved, the optimization mechanism analysis is first conducted in this study. And as shown in these figures, for different RP, different spring breakup, the spring breakup is commonly controlled by different optimization mechanisms. And under the mechanical breakup, the spring breakup is mainly controlled by the aerodynamic breakup. And for the external flashing, the flashing boiling happens. And the process of bubble nucleation goes and explosion happens inside the jet. And for the transition and fully flashing boiling mode, the effects of the nozzle flow should be considered. And especially for the fully flashing boiling mode, the spring breakup is dominated by the nozzle flow. And the status involved in this study is then recognized using different transition criterion and experiment results. The first criterion is based on the nuclear energy barrier, and through the calculation, it can be seen that the condition with RP 0.1 is located as the transition region, which needs to consider the in-nozzle flow effect. And the second criterion is based on the surface boiling and fluid dynamic characteristics through the calculation of Jacob and Weber number. And the calculation result is shown in this figure, which gives us similar results with the first criterion. And the third criterion, just based on the RP, we also can conclude that the condition with RP 0.1 is shown with significant effect of the nozzle flow. And final is based on the experiment results. And as shown this backlight image in the experiment, we can conclude that the condition with RP 0.5 and 0.3, the bubble goes and exploring works. And under the conditions with RP 0.1, the spring width and experiment rate increase significantly, which means that this condition is located at the transition and fully flashing boiling area, needing considering nozzle flow. Therefore, based on the above optimization mechanisms, we can conclude that for different dynamic conditions, different spring breakup modes should be used. And in this study on the normal evaporation region, the aerodynamic breakup model is used. And for the external flashing boiling region, the thermal breakup model is added. Finally, for the transition and the fully flashing region, the boundary conditions including the initial droplet size, velocity, and spring angle is further optimized, and wherein the thermal breakup model and the optimization boundary conditions are implemented in OpenFOAM version 8. And the next part is about the model construction and computational details. The spring model development and the large eddy simulations of liquid ammonia injection is conducted under the OpenFOAM version 8 based on the Euler and Lagrange scheme. And the governing equations of gas phase, including the mass, momentum, species mass fraction, and enthalpy conservation, are shown in the left part, wherein the S, rho, U, Y, K, H are the interaction system of liquid gas phase, and the subgrid strength tensor is modeled by the K equation, and the subgrid species mass fraction and the enthalpy flux are modeled by the gradient diffusion hypothesis. And then the governing equations of Paso and some sub-spring model are shown in the right part, and it is worth noting that the Ricci-Walker model is used as the aerodynamic breakup model in this study. And for the computational mesh, in order to resolve the sufficient turbulence kinetic energy and simultaneously ensure the computational efficiency, the 0.125 mm mesh size is for the liquid core region, while the 0.25 mm is for the spring region. And the mesh independence validation is conducted under the RP 1.5 conditions. And as shown in this figure, it can be seen that the present mesh, medium mesh, can give the proper prediction results. And then is for the introduction about the external thermal breakup model and optimization boundary conditions. First is the thermal breakup model. In this model, the process of bubble nucleation, goals, and exploring are modeled. The critical bubble radius is used as the initial bubble radius, and the RP equation is used for the bubble goals. And then based on the instability analysis and the mass conservation, the breakup criterion and SMR of child droplets are obtained. In this model, it assumes that the breakup happens when the thickness of liquid film is equal to the instability amplitude. And due to the bubble goals, the velocity increase of child droplets also considered. And that is the effective nozzle model for the initial size distributions, which quantifies the heterogeneous nucleation in nozzle through zero-dimensional model. And as shown in this figure, through the calculation of bubble departure, diameter, and frequency, the volume of the vapor in the nozzle exit can be obtained. And in this study, the normalization droplet diameter reduction factor is used. And then for the spring angle correlation. In the experiment, it can be seen that due to the bubble breakup in the near field and the faster evaporation of small droplets in far field, the spring angle shows increase first and then decrease trade, which shows the leaf plum shape. Therefore, the time-varying spring angle correlation is also used in this model. Besides, due to the superheated in-nozzle flow, the velocity increment also be considered in this study. And in this study, the initial droplet velocity is the sum of the pressure driver velocity and the velocity increment. And the discharge coefficient is based on the Reynolds number. And the third part is about the model comparison and evaluation results. The first is under the normal evaporation region with condition with RP 1.5 and 1 condition. And as shown in these two figures, the present model, considering the aerodynamic breakup model, can give the proper prediction results for the spring penetration and morphology. And the second result is for the external flash and boiling region under the RP 0.5 and 0.3 conditions. The present model and traditional rigid work model are compared in this part. And it also can be seen the present model, considering the external thermal breakup model, can give the better prediction results for the spring penetration and morphology, which mainly results from the initial droplet size distribution. And the third evolution is for the transitional and fully flash and boiling region on the RP 0.1 condition. The present model in this work, thermal breakout model without optimization boundary condition and the rigid work model are compared in this part. The further optimization of boundary conditions include the initial droplet size, velocity, and spring angle can give the best prediction results, which indicates the importance of considering the in-nozzle flow in this condition. And the final part is the conclusion. First, the high saturation vapor pressure of liquid ammonia introduces wide thermodynamic conditions from normal evaporation to fully flash and boiling in practical applications. Second, the optimization mechanisms analysis for different conditions is beneficial for the construction of unified spring model. Third, the thermal breakout model and optimization boundary conditions under the Euler-Lagrange schemes are implemented in the OpenFOAM version 8. Finally, the present model in this work comprehensively considering the in-nozzle flow with heterogeneous nucleation, external thermal and aerodynamic breakup model obtains proper prediction performance under wide thermodynamic conditions. And that's all. Thank you for your attention.